Hi everyone. So today is the first day reviewing for the epi chemistry. So we're going to start with the multiple choice question for unit 1. So let's start doing the first question. Okay, so what element does this spectrum represent? So we can see that on the y-axis, we have the relative number of electrons. That means how many electrons there are, right? So if you have something that is short, that means you have lesser electrons. As the height goes up, that means you have more electrons. While on the x-axis, we have binding energy. That means the energy required to release electron from the atom. So if you really notice, you can see that the binding energy is actually decreasing, right? So you start with 100 here, and then as it goes to 10, 5, and gonna be lower and lower as it goes. What does it mean? It means, let's say you have a orbital of 1s versus 2s. Which one of these two orbitals gonna have higher binding energy? So the answer is 1s. Why? Because 1s is more closer to the nucleus. So when it is closer to the nucleus is going to held it more strongly when compared to something that is a bit further away, like the 2s orbital. So as we can say, because this is having the highest binding energy and the closest orbital to the nucleus is the 1s, we can say probably this is the 1s, right? So I'm going to start with 1s here. And then you can do 2s, 2p, 3s, 3p, right? Now we're going to give the electrons. So the electrons we're going to put as the power to these orbitals, right? So this we can assume it's going to be 2, right? Because s orbital can have until up to 2 electrons. So basically this is full, right? Look at this. This is also the same height. So this is also probably 2. The amount of electron that can occupy, the maximum amount of electron that can occupy a p orbital is 6. So probably this is a 6, right? I'm going to give the 6. Again, 3s is going to be 2. Now, look at this. Are we going to give 6 here, right? Because wait, we know that this is the 6. It's supposed to have this much of height to be 6, right? But it's kind of just half to the height, right? Just here. Basically, it's going to be more than 2 because this is the height for 2 electrons. So probably 3, right? So we have our electronic configuration, which is 1s2, 2s2, 2p6, 3s2, 3p3. Now we can look at the periodic table and figure out which element we're talking about now, right? So 3p3. Which one has 3p3? So 1s2, 2s2, 2p6, 3s2, 3p1, 3p2, 3p3. So the element that we're talking about is the phosphorus. So the answer is phosphorus. Okay. Which peak represent the 2s subshell? So the 2s subshell is this peak, 6.84. An electron from which peak would have the greatest velocity after ejection? Okay, think about this. So when we have, right? Okay, let's say you give the same amount of energy to all this subshell, right? To all these subshell, give the same amount of energy, right? Which one's gonna require more energy just to what? Just to get out of the atom? The 1s, because 1s has the highest binding energy. And the lowest orbital that need the energy to get out from the atom is actually the 3p, right? So think about this. If you have if you give the same amount, let's say you give 100 here. Okay, I'm just not. Let's say you give 150 here. I'm just saying 150 megajoules to both of this, right? When you give 150 megajoules, 100 joules, 100 joules gonna be required just to get out the electron from the 1s, right? So minus 100. So you're gonna still have 50. But for this one, it's just require 1.76. So you're still gonna have about 148 point blah, 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 right? Maybe 24. There you go. So the leftover energy in the 3p is gonna be higher. And that energy can be used for kinetic energy, right? And what is the formula for kinetic energy? Kinetic energy equals to half mv squared, right? The mass gonna be the same. So the higher your kinetic energy, that means what? You're gonna have higher velocity. That means you're gonna have higher speed. So electron from which peak would have the greatest velocity after rejection? So the answer would be the one with the lowest binding energy, which is the 3p 1.76. How many valence electrons does this atom have? Well, we already figured out what kind of atom it has. So the valence electron would be the outermost shell. So we have the outermost shell is 3, right? The third principal quantum the principal quantum number, right? So 2 plus 3 gonna give us 5. Okay. Going to the next one. Why does an ion of phosphorus P3 minus have a larger radius than a neutral atom of phosphorus? When we have phosphorus, right? Let's just draw the Bohr structure for phosphorus. So we 1, 2, 3. So gonna have 2 here, 8, and you're gonna have 5. So this is a neutral atom, right? When you have P3 minus, that means you're gonna have an extra 3 electrons. So let's just copy this one, and we're gonna put an extra 3 electrons here. Minus 3. Okay. So think about this. The phosphorus itself has 15 proton in the nucleus, right? Those protons are the one that's gonna help all those electrons to itself. But when you have an ion with the 3 minus, that means you have extra 3 electrons. The proton is going to be having a very hard time to what? To pull or to help the extra electrons, right? So that's the reason it's going to what? It's going to be bigger. Okay, if we talk in chemistry terms, we can say it's going to have more shielding effect. Okay, so yeah, let's check this one. Why does an ion has larger radius than neutral? There is a greater Coulombic attraction between nucleus and the electron. No. So that's wrong, because we know that the attraction would what? Would decrease as you add the electrons, right? So that's wrong. The core electrons in P3. So what is the core electrons? The electrons below the valence shell. That means the second one and the first one. The core electrons in P3 exert a weaker shielding force than those in a neutral atom. Well, this sounds like if you just look at the shielding force, you would think this is right. But look carefully, see the core electrons. So when we talk about the core electrons, we're talking about this, the first shell and the second shell. And if you look both of these, the atom and the anion, both of them has the same exact number of electrons in the core electrons, right? In the core shells. So this is also wrong because they actually have the same shielding effect if It is in terms of the core electrons. So that's wrong. The nuclear charge is weaker in P3 minus than it is in the P. Well, that's wrong either, because we know that both of them has 15 proton, but they have 15 nuclear charge. So that's wrong. And the last one, the electron in P3 have greater Coulombic repulsion than those in neutral atom. Okay, now that has something to do, right? These electrons, right? You have these extra electrons, and these extra electrons is the one that is going to what? Is going to repulse from each other. Not just the protons gonna have harder time to keep this stable or keep this in place. They're also going to what? They're also going to repulse each other because electron has what? Negative charge. So the answer would be D. A compound is entirely made up of silicon and oxygen atom. If there are 14 grams of silicon and 32 grams, what is the empirical formula for the compound? Okay. So to do the empirical formula, there are step-by-step things that we have to do. So we start with making a table. So this is made up of what? Silicon and oxygen. So we're gonna make a table of silicon and oxygen. So the first row is going to be the gram. We know that we have 14.0 gram of silicon and 32 gram of oxygen. The second one, we're gonna calculate the moles, right? So mole is what? Gram divided by the molar mass. So going to look at the periodic table to figure out the molar mass. So we have, for silicon, we have 14 gram divided by the molar mass of silicon, which is 28.09 gram per mole, because the unit for molar mass is gram per mole. And then we do for oxygen. So 32.0 gram divided by molar mass of oxygen, which is 16.00. Doing this, we can find out, you can use your calculator too, and we're gonna, you can use your calculator too, and we can find the number of moles. So we have 14 divided by 28.09, we have 0.4984 moles. And here we have 32 divided by 16 is 2.00 moles. Okay. The third step is to divide by the lowest number. So the lowest number is the 0.4984. So divide both sides with the lowest number. The lowest number. So we have 0.4984 divided by 0.4984. And this one's going to give us 2 divided by 0.4984. This one we have 1, and this one we're going to have 4.0128. So as we can see, this, if we convert this, because this is very near to a whole number, we can just say this is 4 and this is 1. So our empirical formula would be silicon O4. So the answer is B. The diagram below shows the relative atomic size of 3 different elements for the same period. Okay. So as we can see, the size becoming smaller, right? And they are in the same period. When they're in different period, right? Let's look at the periodic table again. Okay, so we know that the size becomes smaller as you go from left to right, and it's going to become bigger as you go from top to bottom. The reason, well, the easiest reason is the one going from top to bottom, because as you go to the bottom, you're adding another shell. As you adding more shells, it's gonna become bigger and bigger. So the first period, you only have one shell, right? In the second period, you're gonna have two shells. Of course, it's gonna become bigger. In the third period, you're gonna have three shells. So bigger and bigger. It's gonna be bigger, right? So that's the reason why it becomes bigger and bigger. But when it is in the same period, what makes it become bigger, right? Because they're having the same number of shell. So let's say we want to compare between carbon, nitrogen, and oxygen. So what we see is the atomic number. The atomic number for carbon is 6, nitrogen is 7, oxygen is 8. The atomic number is also telling us the number of proton. That means we have 6 proton for carbon, 7 proton for nitrogen, and 8 for oxygen. Because there is increase in amount of proton, that means it's going to have a higher attraction towards the valence electron. Because it's gonna have a stronger attraction, the valence electron is going to move closer. It's going to move closer to the nucleus, means it's the size going to reduce. Because there is increase in number of proton. So that is the reason the effect. So for number 7, let's see, which statement must be true? The effective nuclear charge will be the greatest in element X. Now, as we see, let's say this is carbon, this is carbon, nitrogen, and oxygen, right? And we have 6, 7, 8. So the effective nuclear charge would be greatest in element X. That's wrong. We know it's going to be more in the smaller one. It's going to have higher attraction. The first ionization energy will be greatest in the element X. Well, ionization energy means what? The energy required to lose the first electron. So if you have a smaller atom, that means it's going to require more energy just to get rid of the first electron when compared to a bigger atom, because the electron is far away. So if we talk about the Coulombic attraction, the attraction will be more when you have a shorter distance. This one is larger distance, so the attraction or the energy request is going to be lesser. So it's going to have higher in Z. And that's wrong. The electron shielding effect would be greatest in element Z. So shielding effect is, okay, so the higher is your shielding effect. If you have higher shielding effect, that means you're shielding the charge of the proton to have the attraction with the valence electron. So if you have higher shielding effect, the attraction between the nucleus and the valence electrons is going to be weaker. If it's weaker, it's not going to be smaller. It's actually going to be bigger, because there's going to be less of attraction. So it's going to be bigger, right? So the one with the greatest shielding effect must be in X. Why? Because it's bigger. So this is also wrong. the electronegativity value will be greatest in element Z. Okay, we know that when you have what? A smaller atom. A smaller atom, what is electronegativity again? It is the ability to pull electron. So if you have a smaller atom, that means you have higher proton. If you have higher proton, you have higher effective nuclear charge. So the nuclear charge can hold a new electrons, right? Or it will be holding the extra electrons. So it would be D. The first ionization energy for a neutral atom chlorine. So what is ionization energy again? It is the energy that is going to be added for an electron to be released. So the first ionization energy for a neutral atom of chlorine is this one. And the first ionization energy for neutral atom of argon is this one. How would the first ionization energy value for a neutral atom of potassium compare to those two values? So let's look at the periodic table again. So we have the chlorine, argon, and potassium. Chlorine, argon, and potassium. So we see the chlorine is having a smaller ionization energy when compared to the argon, which makes sense, right? Argon is a noble gas, so it has the full octet. So it's going to be harder to release the electron from a full octet or from the noble gas. So this one's gonna have higher ionization energy when compared to chlorine, right? But when we compare to the potassium here, right? Potassium gonna have what? The configuration is argon 4s1. So it's going to be easier for it to release the electron, the extra electron, because first it is in the fourth period. The electron is on the fourth period, which means it's very far away from the nucleus. And also there is only one and it's metal. So it's easier, they tend to lose the electron when compared to chlorine, because chlorine, the configuration for chlorine would be neon 3s2 3p5. So instead of losing, the chlorine would want to have an extra electron. They would want to have extra electron just to fill the octet. So it's gonna be harder for chlorine to lose electron when compared to potassium. So number 8, it would be greater than both because potassium carries greater nuclear charge, so that's wrong. It would be greater, we know it's gonna be smaller, so that's wrong. So it's either C or D. It would be less than both because there are more electrons in potassium. Well, that's not the reason, right? It will be less because a valence electron of potassium is farther away from the nucleus than one of either chlorine or argon. So that's the reason. Number 9, a neutral atom of chlorine are bombarded by high energy photon, causing the ejection of electrons from the various filled subshell. Electrons originally from which subshell will have the highest velocity. Okay, we talked about this. The one with the highest, like okay, first, before we even talk about that, let's write down the configuration for potassium. Oh, sorry. Sorry, it's talking about chlorine. So we're gonna write down the configuration for chlorine. So we have 1s2, 2s2, 2p6, 3s2, 3p5, right? That's the configuration. So what is the lowest energy? This is the 3p. So C. And the last question, the average mass in gram of 1 mole of carbon is equal to, so this is a definition. Okay, so 1 mole of carbon, right? 1 mole of carbon, it has 12 gram per mole, right? So the average mass of a single carbon atom measured in AMUs. That is right. This is the average mass. The ratio of the number of carbon, no. So you want to know that 1 AMU, right? 1 AMU is equals to 1/12 of the mass of carbon 12. This is the isotope because we know there are different isotopes of carbon, and one of them is carbon 12. So 1 AMU is the mass of carbon 12 divided by 12, which is kind of confusing because you see, you have 12 here, 12 here, but it's just like divided by 12. The mass of carbon 12, which is an isotope, divided by 12. That is still 1 AMU. So for one single carbon, the average mass will be measured in MU. That is right. Okay. So that's it for today. I'll see you later with more questions. Bye-bye.